Hello everyone, welcome back to Calculus. This time we are moving to our third big topic in calculus. It's about integrals. To get us started, let's consider a very simple question: how to find out the area underneath the graph of a function, like the drawing over here. This is the curve, it is the graph of the function. And we are considering the area underneath the graph and above the x-axis for x running from A to this point x sub 4, it is B, for x running from A to B, okay. And well, as you can tell, this is not a normal shape. It's not a common shape, not a regular shape, rectangle or circle, those things we can handle. So to answer this question, well, we somewhat, we know we don't have the answer exactly for the moment. We try to give an estimate. So the way to estimate here is, we divide this region, the region underneath the graph of the function over the x-axis for x running from A to B into four small parts. And also to simplify discussion, let's say for each small part, we have the length of the panel controlled at the same, which is denoted by delta x. And in this case, because we are considering the area running from x equals A to x equals B. So the delta x in this case, indeed, it is just B minus A over 4. Okay. And then after dividing this entire region into those small panels, and we say on each panel, it can be approximated by a regular shape, a rectangle, like clearly in the panel, for the panels in the middle. I think it's very reasonable to say, right? The area of the actual panel turns out to be the area of the rectangle, very close. And also for the fourth panel, I think it's still reasonable to say the area of the panel, it is about the area of the rectangle. And the same for the first one. And then if that is the case, when we add the areas of those rectangles together, it would be the estimated area for the region we want, right? And then let's take a quick look. What about the area of each rectangle here? As we said, we want to keep some control. Keep the discussion simple. So the width of each rectangular panel, it is of the same, which is delta x. And then the area, look at this rectangle here. Would it make sense to you? The area of the first rectangle would be the function value at x1 times delta x. So indeed, it is right here, f of x1 times delta x. And similarly, the area of the second rectangle, it is f of x2 times delta x. Same for the third one and the fourth one. Add them together. We also use a sigma notation, right? Even though in this case, sigma notation may not be very helpful. We are just adding 4 terms. But anyway, you will see, very soon we are going to add more terms. Indeed, we are going to add more and more terms. So we want to use the sigma notation to denote the approximation. This is the approximated area for the area underneath the graph of the function for x running from A to B and over the x-axis. And clearly, as you can tell, well, this approximation can be improved. The approximation can be improved. The way to improve the accuracy here is instead of dividing this entire region into 4 panels, how about we separate into 8 panels? 8 panels, okay. And it looks like it should be somewhat a better approximation compared to the first approximation we did. And then indeed it can be verified numerically. But anyway, for this class, I'm going to skip the detailed calculation here. Okay, I'm just saying by dividing the panel into more smaller panels, the accuracy of the approximation can be improved. Indeed, it can be improved a lot. So accordingly, this time this is how we calculate the area, estimate the area using 8 rectangular panels. And using the sigma notation, it's about the same, right? You just change the upper bound from 4 to 8. But anyway, indeed, it is verified. The accuracy improved. And furthermore, we can keep on improving the accuracy by dividing the separated region into more and more rectangular panels. And this is the case when we divide the region into 32. Simply by checking, by looking, you see, it doesn't make sense to me. Well, when we have more smaller rectangular panels and the actual shaded area, it is really getting closer to the sum of the areas of the rectangles. It's just true. And besides, really I want you to know, the accuracy can be improved by dividing the rectangular panel into more smaller panels. And then we said that we have a limit, right? Indeed, we could calculate the limit at infinity. If let's just pretend that we can divide this into infinite number of smaller panels. So this sigma notation turns out to be a limit. It turns out to be a limit. And you want to understand that this sigma, first of all, it's harder to handle the sigma notation, and also combined with the limit notation, it is very complicated situation, very complicated thing. But anyway, if we do it carefully and in some special cases, we can handle it. And indeed, it's being proven and it's being verified. And this calculation, it does give us the area exactly. And this kind of calculation, certainly it will answer the question of the area underneath the graph of the function, and also it has many different applications. So we call this kind of a calculation as an integral. The limit of a sum, by the way, it's worth to mention, a sum like here, or like we discussed it in the very beginning, with 4 rectangles, with 8 rectangles, with 32, with 64, with 100 or more. These are called the Riemann sum. And then the limit of the Riemann sum, it is defined as an integral. And we write in the following fashion. I want to see this closely, okay? We are adding many terms, and we are adding infinite number of terms. It's a sum, that's an infinite sum, okay? So the limit part and the sigma notation together, it simply indicates we are having an infinite sum. Sum, the keyword is as. So we want to make sure the sum, it is long enough. So this integral notation really it is somewhat elongated as. The limit and the sigma notation indicates that the infinite sum. Simply it is replaced with the very tall s here. That's the integral sign. We are considering the area for x running from a to b. A is the lower bound, b is the upper bound for the integral. And also be very careful about this f of x dx. Okay, I really want to say here is the do consider f of x dx, f of x dx as a product. Because if you remember, we have a lot of those things, right? F times delta x, F times delta x. Basically, F times dx, it's a product. It denotes the area of a rectangular panel. Any rectangular panel, it is calculated in the same fashion. But anyway, at a different point value of x, the area would be different. So we are adding them together. So this is formally the integral sign. And when you write the integral sign, do not forget put the dx in the end. Later on, we may have dy, du, dt, some other variables. And you do need to put dx, dy, dt, those things in the end. That is the integral. Without the dx in the end, it's nothing. Because dx, really, it is part of product, right? Delta x. dx, it is direct used to replace delta x, which is part of product. You cannot remove any part of a product, still claim it is the same thing. It's not. Okay. So this is the correct way to write a definite integral. It's a definite integral. And I hope you see a definite integral. One way to consider definite integral, it is the area underneath the graph of the function for x running from a to b and above the x-axis, okay? And it is calculated, the Riemann integral, it is defined as the limit of the Riemann sum. And usually it is hard to handle the limit of the Riemann sum. So the next part, we will try to explain how do we find out a definite integral. So this example, it is from the textbook directly, 5.8, and calculate the definite integral. And you may wonder, this is a very strange thing, right? It is. But anyway, look very closely, okay? First of all, I suppose we do understand that this will have to be the area underneath the graph for x running from 3 to 6. And if you wonder what kind of area is this, what is the shape of the graph, how the graph would look like. So this is how you want to handle it. First of all, because of square root, you want to take out this function. By the way, I suppose you know, this is the integrand. The definite integral notation, it is very similar to the antiderivative notation, right? Or the indefinite integral. It is. F of x in the middle, it is the integrand. So you may want to simply take out the integrand, consider that a function. Because of the square root, and you want to square both sides. And if you make the arrangement, put those two perfect squares together, I realize this is really the graph of a circle with radius 3, centered at the point 3 and 0. And then, because x is running from 3 to 6, we are not having the entire circle. We are only having a quarter of the circle. Besides, you may want to know, as I'm saying, this is not even half of the circle, it's a quarter of the circle. Y is a square root, which means y is positive. Okay. At this point, we are considering the half circle above the x-axis. Because the restriction of x running from 3 to 6, we know it's just quarter of the circle. So according to the area formula for the circle, this integral is the area of this quarter of the circle. Area of the circle, that's pi r squared. A quarter of a circle, that's 1/4. That is it. That is an integral, a definite integral. If any chance you can calculate, you know the graph, and you can calculate the area from the graph, calculate the integral from the graph directly. And also another example, it is checkpoint 5.9 from the textbook. And it is just true. Usually we consider, and indeed I say this a lot, we consider the integral, it is the area underneath the graph. But anyway, you may want to know it is possible. You may have the area above x-axis, and you may also have the area below the x-axis. So indeed, checkpoint 5.9, it shows you the case. Okay, it shows you the case. The lower part of the area, it is above the x-axis. Part of the area, it is below the x-axis. And then the integral, it turns out to be, it is always the area in the upper part, okay? The upper area minus the lower area. And in this case, because the upper region, it is a triangle, right? The lower region, that's also a triangle. So we can calculate those areas together. And we get the integral as 6. And also, I really want to know, it is possible you may have an integral turns out to be negative, because you could have the situation, the lower part of the region, it is bigger than the upper part of the region. and then the integral, it is negative. But anyway, if you are calculating an integral using the area approach, keep in mind it is always the area on the top minus the area at the bottom. And also another quick reminder here is keep in mind area, it is always positive, and then integral, you need could be positive, could be negative, also could be zero, could be zero. So this is the beginning of the discussion of a definite integral. A definite integral usually represents an area. It represents area, and it is defined as the limit of the Riemann sum. And also, I really will have to say, in some rare cases, okay, in some, well, maybe in some simple cases, if you can identify the graph and then you know how to calculate the area directly, then you may be able to tell the definite integral using the area approach. But anyway, don't take it for granted. Indeed, to evaluate a definite integral, we are having somewhat very efficient result. It is the fundamental theorem of calculus. But anyway, we will consider the fundamental theorem of calculus in the next part. Thank you for watching.